Welcome back after last of our intermissions. And we are ready for last but not least of our speakers. Please remember to use the conference app to rate every speech to help us improve for next editions. All right, our speaker is already on stage, of course. So quick introduction. With 18 years in the industry, making his first steps in Java in messaging applications, working on various projects within one company, yet renamed a couple times. Over the last few years, focused on cloud world, Kubernetes, and open source security, and after moving to R&D management, still trying to code a bit. I love this fun fact about Jarosław, because this is our speaker, of course. During free time, trying to tame a couple of grass frogs. No success so far. Fingers crossed then.
Well, they went asleep already. Thank you.
In the speech entitled From PaaS to SaaS, Building Automated Ordering System on Multitenant Kubernetes Platform, please welcome to the stage Jarosław Górski.
All right. So, and now for something completely different than the speeches today. A little background. I work for cloud and network services business. And this part is called Common Software Foundation. This common is a key word for today. And I'm here thanks to our NCBR, Narodowe Centrum Badań i Rozwoju. Here is the information from the government portal. It's in Polish, so let me translate it a bit. It's about creating a multi-tenant innovative platform that is highly available, scalable, and able to run automated ordering process in SaaS model. We've received a grant from European Union on it, and we ended this journey last year, and I'm happy to share a few of ideas that we were working on. It mentions also optimization of the cost. The cost is always important, and configuration simplification to reduce development time. A short agenda, what I'm going to talk about today. The first thing is rationale behind the project. Why did we do it? How did we do it? Then I'm going to talk about multi-tenant services, how we achieved multi-tenancy on various services. Then a couple words about templating. Templating of the configuration of the installation to simplify things. Next, staying alive, so a couple of non-functional system requirements that system engineers love a lot. And finally, how SaaS application runs on this platform as a service environment. First, a historical background, how the applications evolved to the microservices world. We all started with old-fashioned bare metal world where applications were monolithic. Then at least part of us, and we have hundreds of applications in Nokia, went through the virtualization phase where we still had monolith, maybe some decomposition happened already. And finally, we are now in the cloud world where we have microservices. We decomposed everything into small pieces, and at least in our case, we run everything on Kubernetes. By the way, how many of you are familiar with Kubernetes? Okay, that's a lot. So you know that it's an ancient god of spending money on cloud services, right? I read it somewhere. Well, he'll be around here while I'm talking about the services, so we'll touch upon some of the concepts in Kubernetes. Okay, why do we do it? The first thing is that we have a lot of testing and development environments. Developers are greedy. They want to have environment for their own. They want to break it. They want to forget about it and just use it a week after. Also, the decomposition of the services led to splitting the small parts that do the same thing for various applications, and it's even more waste because we don't reuse them. We bring their instances for our own. And last but not least, SaaS ordering system needed to have a multi-tenant environment because of its nature. And speaking about the costs, because this is important, A yearly annual cost of one cluster, one typical cluster that has 100 CPUs in cloud environment can cost about $40,000. It's not only a cost of VMs, it's about control plane, about surrounding services, exposing it, gateways, and so on. And how many application instances do you need today? Is it 1 or 2 or 5? There are various purposes. So the idea was to share the environment, to reuse the same clusters. And there are various use cases. One of them can be a playground. Developers or people wanting to sell something to other teams need sandbox environments. They need proof of concept environments, demos, or just to get familiar with something. They need environment for that. Development is very important. Everyone wants to have own environment, so we need a lot of clusters. Then QA comes in, and there is a pre-integration phase, integration, official integration, continuous integration, all kinds of integration. Performance labs maybe are separate, are a different case, but in other QA cases, we can share environments. And also, in some cases, customers do want to share the environments. For example, you can have testing environment plus the pre-production environment hosted on the same cluster. Some can say, all right, but cloud environment can be cheaper. You want to have savings, you can do it actually. Well, in a 3-year plan or 1-year plan, so you need to invest, you need to have a subscription. And that comes with a cost, because you don't know if in 2 years from now, your application will need still these resources or not. They can be reused in some cases, but in some other, they cannot be. So we needed more freedom. And important things were also environments when we can run our platform. One of the more popular environment is our own Nokia Kubernetes service and CS. But that's not the only one. We focused also on AWS EKS or VMware Tanzu. And the goal was to have services shared but isolated enough so that applications do not break other applications' data or do not even see it. And of course, we needed to be flexible, highly available, automation is the buzzword, or every other thing that system engineers can imagine needed to be there. We looked at our competitors, we looked at some community projects. One of them was OpenShift projects. It wasn't good enough for us at the time. There were also special interest groups where there were hierarchical namespaces. However, it was not a complete solution. So this led us to the vision of platform as a service. Platform serving components in a safe multi-tenant way. And there can be various multi-tenant services. It can be telemetry, access control, authentication service, notifications engine, logging engine, storage, and many more. Please do not read it. That's my only ask. This is just a high-level architecture. I liked other presentations with, the full architecture that cannot be read at all. This is the same. But in the gray middle boxes, there are multi-tenant services. The green part is our multi-tenant controllers, and the blue part is the cluster-level services. I'm not going to cover all of them, of course, but I'm going to talk about the projects, which is a concept of namespace grouping, about the ports sharing on the cluster, about authentication, API exposure, logs and metric services, registry for the images, and finally, the profiles, so configuration items. How did we write our microservices? Well, they are mainly written in Kubernetes' favorite language, which is Go. Except for one big part that is written in Java, Compass Manager. We have all the services written in Go because they are small, they're quite efficient, they get up quickly. That's not even a half of what we developed. There are a lot of webhooks or custom resource controllers. If you know Kubernetes, you know that custom resource definition is an API contract, a way of defining custom things in Kubernetes. So we use this concept a lot. And the first, most important concept is the project. What it is? It is cluster scoped custom resource that is created to group all the namespaces for one product, which means a product can have one namespace for some functional needs, one for some business specific logic, another for common services that are not business-like. We can have image and chart registry. Helm charts are our way of defining configuration and deployment items in Kubernetes world. So we need a harbor service, which is given for a project. We can have external ports, like TCP or UDP traffic. You can define resource quota, custom access to block traffic between the projects or the namespaces. And you can have profiles installed inside of this project, so a group of charts that is representing the whole product. And access control can be done on namespace level, on project level, or namespace project level. It is, of course, CNI dependent, not all CNIs support it. Here is an example. Because we are on Code Dive, I want to show some things that at least look like a code. Here is an example of a custom resource that is called project. And it's a name DBP. It has some backup quota, Docker quota, resource quota. And then we have a namespace. And each namespace in a cluster needs to have its own project. It is defined by a label. And this label needs to match the project name. In fact, we do not allow any namespace to be created without a project. Then the controller, custom resource controller, adds an owner reference to this namespace so that it has its parent, which is a project. Of course, this is for developers. For the regular users that want to just deploy the service, we have a GUI that can have everything defined on a nice-looking forms, where you can define a project with its scope, whether it's restricted or permissive. If it's restricted, you can have a whitelist of namespaces and projects that can access your project. Then you can have a set of quotas for requests, for limits, for PVCs or storage, and finally for Docker registry slice. Last but not least, ports are important. HTTP is simple because it is just ingress controller. But for TCP UDP, it was a bit complicated. And if we are talking about ports, they can be both project-wide and namespace-wide. We came with a concept of transport ingress CRD that is, at least with the name, similar to the ingress object in Kubernetes, but it's more like a Kubernetes service. Inside a project that you have on the cluster, you can have a cluster port range, which is a custom resource that is cluster-wide. Inside of it, it can have one or more port ranges, a subset of ports that are defined in the cluster port range. And the port range, which is namespace scoped, can have transport ingress objects defined in applications Helm charts. And it can be both TCP or UDP. Here is an example of how these ports objects look like. So we have a cluster port range, which is a cluster level object. It has an owner reference that is a project, so it has a parent. And it has also a pool of ports, a range between minimum and maximum. Then the port range in a namespace has parent of this cluster port range, and then a subset of these ports pool. Application defines just the transport ingress object with a target port and target service. Then this gets translated into Nginx configuration. Because there is one Nginx as ingress controller, we can have configuration part for our application inside this one common configuration for Nginx. So controller takes care of translating this transport ingress object into the Nginx configuration. Next important service was Harbor, so Docker and chart registry, because applications in an on-premise or cloud world do need to have its own local registry for their artifacts, for images and for charts. We did the mapping of Harbor project to platform project, one-to-one mapping, where we just define the Harbor project with private scope, and we create a custom administrator that is allowed to access this project. How do we access it is defined in authentication service, where you define a group that has a name after the Harbor project, and then inside an nginx ingress rule, we have a snippet that just checks the authentication service, which is Keycloak here, checks if the user is allowed to enter Harbor, whether it has proper group mapping. And speaking about authentication a bit, since we have many applications on the cluster, they want to have separate user bases, which is called realms. And inside each realm, each application has its own independent user base and want to define it in advance. So Helm chart can contain custom resource, let's call it CK realm, where you define just the realm name and the secret name containing initial credentials, which will be generated by the controller. They can be removed after. In that way, application can have access to shared Keycloak. For the API exposure, we have a custom Lua module inside Nginx, so that we have single sign-on, because Keycloak is acting as an authentication service. We control access to all the services, some of them supporting Keycloak integration, some of them not supporting. We need to combine all of them inside one Nginx module. For the APIs of the applications, we have other services that also have custom resource definition for services, routes, or plugins like Keycloak integration. This service is Kong. And another example of custom resources that we created, application needs to have a service to expose itself. Then inside the service, it can have one or more routes. And for each route, an API gateway plugins can be defined. It can be Keycloak integration, which is a common case, but also very simple example like here, where a header is added in the response. So simple transformers are also allowed to be defined using the custom resource. For monitoring, there is a Prometheus as a common service, Prometheus and its GUI performance monitoring. Also, we have homegrown notification and alarming modules. Now, metrics access via GUI is controlled via organizations. There was a Teams feature in Grafana that came in later. For Prometheus itself, there is an issue because it has no multi-tenancy at all. So we added a proxy layer, additional layer, API and GUI for alert rules to be defined per namespace. For alerts and notifications, it is also a bridge between Prometheus and the external monitoring systems. So we need to be able to define trap receivers, to define email accounts that will be notified when something's happened on the cluster. And finally, Kubernetes dashboard, which was integrated with OIDC, so again, Keycloak, to have access only for namespace level. So it looks like this. Inside UI, you have access to the metrics of your namespace. You can see CPU, memory, and any other metrics, but only in a namespace scope. For Kubernetes dashboard, the same. You are allowed only to see objects from your namespace, not the cluster level objects or objects from other namespaces. So it's a matter of access control of these services. For alarms and notifications, alerts are called event rules in our case. There is also a need to have per namespace setup. So we have email notification channels, SNMP traps, and it needs to work in both namespace mode and the cluster mode for the cluster administrators. It needs to work in both cases. In this example, maybe not very well shown, we make sure that each metric has a namespace label added so that you cannot see other namespaces metrics because we add this label in our service as a proxy. Logs. Logs are also important, and it was done by OpenSearch predecessors, so Elasticsearch. And it is all about controlling the access to common configuration. By common, I mean fluentd as a daemon set. It's like Nginx. It has configuration in one big file, and we want to control something per namespace. We cannot allow applications to modify the things inside themselves. So we need to have access control. And the access is done per index. Index is serving logs for applications, and it is split per namespace. I will not show CRD anymore, it's too hard. But in general, it's all about defining the level of logs that can be seen, defining the retention that can be seen, and all of this gets translated into custom resources, and then fluentd has configuration blocks injected into the common configuration so that it can understand all the namespaces, setup. That's about the common services. There are a lot more, but I will not spend more time on them. They are not that interesting. However, the most important thing about our project was also configuration templating, simplifying things. We came with the idea of profiles. Profile is something maybe a bit similar to Helm file or maybe newer concepts, but it's all about addressing umbrellas charts issues. By issues, I mean if there is one chart containing the whole application configuration, it can be very large. And you have a 1 megabyte limit inside Kubernetes. Usually, etcd has this limit. So we cannot grow indefinitely. Actually, our platform chart had to be decomposed very early because of that. So we came with idea of profiles, which is a list of charts, an ordered list, allowing us to define the Helm charts to be installed based on some tags, based on some configuration parameters, and in certain namespaces. So it's all about Jinja 2 templates like Helm uses. So we came with these profiles to control the order, control the parameters, and decide when you want to install the chart. In chart itself, you have requirements.yaml file, but it's simpler than this. Again, how to deal with that many configuration options that they are exposed in Helm charts. Usually, developers want to have everything configurable, so we don't want any hard coding. That's obvious. But we end up with thousands of parameters. And actually, in single values.yaml that represents the whole platform or big application, there can be 10,000 parameters. It's too much. No one would configure them one by one. No one would even know which of them are important and which of them can be skipped. It is important for low-level core service development, but only for that. So we came with the idea of templating the values. Templating also using Jinja. We reduced the number of parameters significantly, let's say 200. It's important for platform development and tuning. It can be used during our development phase or application development when they define their new needs. But finally, for the applications, we need to have another template that is even simpler, just a key value. Application developers do not need so many options again. So we reduce this number to, let's say, about 50. So it's a template over template configuration to list only the things that are crucial for the application and expose only these. So the first stage is the values template, where you have a simple definition, where you can use variables. You can define variables based on this higher level template and then use them This is just like in Helm charts. There is an NCMTPL tool that we created to translate this values template into values.yaml file when the chart is being installed. And this second layer, data template, is about simple configuration where you have key value. You can additionally have things like certificates to be read from the files, or some base64 information, or even a specific YAML configuration for a service. A good example of that is having alarming service configuration, which is very different for each of the customers because they have different EMS, they have different setup for the alarming activities. We didn't stop there, actually. We wanted to have GUI also having nice-looking forms based on parameters that can be configurable. So we came up with values model YAML, an optional file in Helm chart that is OpenAPI based. It evolved from Swagger, now it's OpenAPI, and we have ability to create fields with proper type, with proper description that will be displayed, and you can use many variable keywords to say what is the maximum, minimum value for a field. You can even define an enum list for the selection boxes. You can have read-only fields defined so that application wants to expose something, but not allowed to change it, just to inform. And also, format is configurable, so you can have password or text area fields and even define patterns. So they are validated not only on the server side, but also on the browser side. And it looks like this. We have a service catalog. We just bring up some instance, fill a name, and then we go to a form that allows you to choose between the required parameters, where you have a list of fields to be checked and modified if needed with some default values. You can have all the fields displayed if you want, and for the very experienced developers that do it for their own risk, you can switch to the raw values editing. But the default is the simple setup. Not everyone is a developer, but everyone wants to have an instance brought up. So the templating was very important to speed up the development process and the usage of applications. Then we had a lot of non-functional requirements that are crucial for the platform to be stable and reliable. First thing is high availability. It is in Kubernetes a matter of setting the right number of replicas and switching over between them in timely manner. So we decided to have a few services made redundant, critical services, but also logs, monitoring. Exposing service is very important. Webhooks for custom resources need to run all the time. Why? Because if application creates a new object in Kubernetes, it cannot get an answer that, oh, sorry, our service was down and your object is in unknown state or will not be processed. It needs to run smoothly. Also the management layer, so our Compass manager, our Uber controller of everything in the project's world is highly available. What could be left is CRD controllers. Why is that? They are asynchronous. So they do not need to run all the time. Application expresses the intent by creating a custom resource object. It gets created because webhooks run all the time. But the processing of the data inside custom resource is delayed, usually by a few seconds, sometimes by a little more. But since the Golang services, controllers get up very quickly if they are destroyed, we don't need that, right? We need to save the resources wherever possible. So do not create pods that will consume something and without real gain. And actually we had a lot of fun testing this high availability. We used KubeMonkey, which is a version of Chaos Monkey for Kubernetes. So basically, it's a monkey with a razor that cuts cables. And we did it also manually, so it was fun. So we shut down the VMs in random or mean order to check how services react. And we had a goal of about 30 seconds for unavailability for each service. And usually we had this done easily because a lot of services are small and they get up in a matter of seconds. The only one that had some issues close to the time was authentication service, because behind the service there is a database that is also highly available, but it needs to be switched over. It takes time, so it was about 30 seconds at most. Another feature that's very important for saving cost is autoscaling. We have a horizontal pod autoscaler feature in Kubernetes that allows to define thresholds to bring more instances live or remove them when they are no longer needed and the traffic went down. So basically, all the services had HPA per object added. And the biggest challenge, but also fun, was to define the right levels when to scale up or down. And it can be set up based on CPU or memory, but for some services, it is not that simple. Let's say you have a Java service and you want to have a new pod added. It is probably not that easy to just react to the memory usage, because the memory usage can be high. It's rather garbage collection time that this metric is important. And HPA supports custom metrics, so we use this for 2 services, including authentication. So it's not a big deal when you know what makes sense. For example, if you have a database that is MariaDB and it is in master-slave configuration, it doesn't matter if you add more and more pods, as long as you use only the master for writing, right? And you can see some of the results of this autoscaling testing. This green line shows the new pod being created when the traffic was so high that the utilization of the CPU was too much for the services, for the pods that were running initially. And we defined the thresholds to create new pods and to destroy them after. The blue line here shows the new pod created, and the red and orange bars are for the lower and the higher thresholds. Again here, when the pod is created after the existing pods cross the thresholds, it lives only for some time. When the traffic is utilized and the CPU usage drops below a certain target, the pod gets destroyed. Last but not least, geographic redundancy. We could say a lot of things about it, but one thing that I'm sure about is applications have many, many ideas about how geographic redundancy should look like. How to store their data in a safe way, in a geographical manner. We didn't want to focus on it because applications will always stay with their own method. We focused on the platform configuration. So configuration of all the projects, services, custom resources, all the things that are for the platform, not for the application itself. And GR solution in some small application cases can have more lines of code than the application logic itself. So it's not that simple. And the main challenges are not about the sunny day scenarios, but the rainy ones. On this example, it's a bit complex, but let's go through it. It's a very simple view of architecture of our GR solution, where the configuration request comes from the ingress, goes to the Compose Manager pod, to the GR Manager container responsible for handling the GR traffic. The request is processed inside this pod, and then the result is stored in the database, after which the traffic goes to the replica site, the second site where the GR manager gets the request, the processing is done locally as well. But then both primary and replica site results are stored in the database. I cannot tell it this simpler, okay? But the rainy day cases are interesting because the answers, the results may differ. There can be success on one side and failure on the second one. So there is a watcher that checks for the results, does the reconciliation, does the retries, have a queue to process these differences so that the sites are synchronized in the end. All right, finally, let's go to SaaS, which was the second part of this project and the main user mentioned here. What is SaaS? SaaS can also mean many things. Software as a service involves many various components, modules that form the whole solution. Our part is called self-service portal. What is it about? It is a portal that allows application users to express their needs to create application instances. It consists of two parts. Front end, that is part responsible for the user interface, user experience, which then communicates with the backend for the front end, which, unlike the backend of the backend, is a part that is a bridge between the front end and the open APIs that are served by SaaS. And these APIs are grouped into three management API groups. One is Service Catalog API, which is about catalog resources, managing the life cycle of service catalog entries. Second is orders. So when we have this catalog of services, I want to create an order to have this instance of a service. And you can manage orders, you can add them, view them before they are fulfilled. And when they are fulfilled, there is inventory management API. So there is a service instance created, and then you can see its health, its status. You can update it or even delete it. So that these three groups that are in our context. And how the use case looks like. You have a business owner that wants to have some service created, some application instance. So it expresses a demand. It goes to the platform which hosts SSP, this self-service portal and APIs. After this request is processed through this orchestration and delivery layer that is outside of these clusters, it is a separate entity. A service application can be created on one of the clusters that host platform as a service, and then it can be made available to the end users. So there are multiple application clusters, all of them running platform as a service, so sharing the environment where all the application instances are being created. And actually it can be done for both development purposes and also for production environments. And the use case in SaaS was that main services that were utilized is authentication service, then API gateway for APIs of application being exposed. There is a certificate management thing I didn't mention, but it is also important to secure the traffic. Then monitoring tools and logs were also common. What is still not common for SaaS? Of course, the configuration for all these services that I mentioned, plus the database. They wanted to have it separate. So to summarize the ideas that we needed to implement, the first thing is to share as much as we can. This is because resources are expensive. The second thing is to simplify things. Simplify configuration, simplify installation, so that we save developers time, and we save time, so we save money. And the third thing is to fit into the right size, so react to the dynamic changes of the traffic inside a cluster, to scale the services up or down to reduce the CPU load, and finally, to also scale the platform itself, because it's not only about scaling the services, it's also about scaling the virtual machines, so save the cost at the end, especially in cloud environment. That would be it for my presentation. I hope you found some of these ideas interesting, and I'm happy to answer any questions. Thank you.
Thank you very much. Any questions to our speaker? Yes, we have one.
Hi, I'm just trying to figure out because, somewhat we built quite like similar things in a different environments, but still, I've seen that when creating a tenant, you went with the approach we are giving you a limited subset of the available options, but you have the fallback to like go to the, let's call it row mode, and you can define everything. And in our case, we decided to backtrack from that approach because we did exactly the same thing. But we figured out that, hey, you are wanting to buy a Lego set. And now we will just basically give you a plastic injection mold machine. And like you can, in theory, a malicious actor like could maybe try to use the fact that there are like hundreds, I don't believe we are out like thousands as you are, but hundreds of configuration options, and like surely something went under the radar. We like didn't think about like some clever or less clever thing of like configuring something, and you will break something on our side, and you will like break something on like our scalar, balancer, ingress, like anything. Like how are you mitigating that, or maybe like you're not even like afraid of that, and why?
Okay, so we also started with the same approach. So no, you cannot configure everything, but then we got a lot of application developer complaints, and they wanted to do their development where they wanted to have freedom. For the regular users, this is fine, but not for the application developers. But the thing about security, it is not for the platform instantiation or services, platform services instantiation, only about application instantiation, or the service that is not shared, because the shared services run all the time. These are the private instances. If application developer wants to break something and bring the application instance that is not working, he can do it, but not break the platform itself. But it's rather I don't want to say a backdoor, but an ability for the developers to test a few things, especially when they just create their Helm charts. It is not finished yet. They have not gone through this values model or anything like that. They are just starting. So they need that for that purpose.
Yeah. Okay, thanks.
Thank you. Anyone else? All right, thank you very much then, and give again a round of applause Jarosław for our speech.